All right, so this is going to be 16.6.2. So where did we leave off? In the last problem, we were given a molarity and a pH, and we calculated the value of the equilibrium constant. This is going to be a different scenario. We're going to work a problem where we are given the concentration of a weak acid and the Ka, and we're going to calculate the pH. Remember that all this means here when we calculate the pH is we're going to get the concentration of hydronium ion, or H+, in our acid solution. That's all this is. And so, again, this is a weak acid, so we're probably going to have to use a Rice table to do it. Okay. So the dissociation of hypochlorous acid looks like this. Okay. And the Ka value is going to be products over reactants. Now, the Ka for hypochlorous acid is small. There it is, right? So we're going to use an ice table to calculate the concentration in this molarity of hypochlorous acid. So I've got my initial acid concentration, I've got my Ka, I just need to solve for hydrogen concentration. So let's set this up. RICE, okay, where am I starting? It says that I have a 0.20 molar solution, and I don't have any of my ions. Again, I'm going to shift in this direction. Everything's 1 to 1 to 1. That kind of makes it nice. I'm kind of going a little quick here, sort of bypassing some of the individual steps that I did before. Pretty soon you're going to be able to do these Rice tables so fast you may not even need to draw it out. All right, so what I've got here is I've got a Rice table, and let's go ahead and pop this into my Ka expression. But here's what we're going to do. This is really small. We talked about how small is small. Anything under 10 to the third, the minus third, you pretty much, that's really small. It's 1,000-fold from it being close to 1, so it's really, really, really reactant favored. So if I have 0.2 of this, and this goes to 8 decimal or 7 decimal places, this is negligible. So I don't need to worry about that. So what I'm going to do is I'm going to use the same concept, looking at that small value for this. And when I plug this in, I'm going to assume that X, sorry, this should be O2, apologize for that. O2O is negligible, and I'm going to set that equal to 3.0 times 10 to the minus 8. If I solve for X, which is also the hydrogen ion concentration, isn't that what I'm looking for? If I want the pH, that's what I'm looking for, is equal to 2.4 times 10 to the minus 5 molar. The negative log of 2.4 times 10 to the minus 5 is equal to 4.62. Remember, I've got two significant figures in my data here, 1, 2. So I'm going to go 2 past the decimal point, and that's going to be my pH. Now, we're going to look at what percent dissociation we have, because we can use percent ionization, same thing, to find out whether or not our removal of X was justified, right? Because if it turns out that our percent dissociation is small, then I can use that. So it says, as a general rule, if the percent ionization is less than 5%, the initial concentration of acid, then we can make that simplifying assumption that allows us to avoid the quadratic formula. Yay! All right. This section discusses the assumption and how to check its validity. So let's do that. So my percent ionization is what? It's going to be my change. So let's go back over here. What was X, right? There's X that's my change. That's how much dissociated, right? That's how much acid went to ions. So that's going to be 2.4 times 10 to the minus 5 divided by what my initial times 100, and that's going to equal to 0.21%. So that's good. That means that I could, that if it's below 5%, then I was allowed to cross off that X. It's just not significant. Now, what we want to do is compare these two acids. We just took the percent ionizations of nicotinic acid, had ionization was 2.8%, and the pH was 3.23. For the hypochlorous acid, all right, I had 0.21% and a pH of 4.62. All right, so if I'm comparing these, which of these two is a stronger acid, then I'm going to look at the pHs, yes, but also the percent ionization. What this tells me is that more of this acid dissociates to products, which are the ions, than this one does. If this dissociates more, I'm going to get more H+. Therefore, I'm going to have a stronger acid. Okay? So that means that nicotinic acid is stronger. Not just because you could notice it with the lower pH, but my percent ionization. So, the larger the Ka, the stronger the acid. The stronger the acid, the lower the pH, and that's just always hard to remember that. So what I'm going to do is some really quick rice table calculations. I think what I'll do here is that I'm going to do one of these with a real quick rice table, and that's how we did all of them. And then if you need help going back to determine, you can do that. Basically, I've got a Ka here, and I've got my initial concentrations. So basically, I'm going to calculate my hydrogen ion concentration by calculating X and then finding my equilibrium concentration and then finding my pH. Okay. So my Ka, I'm going to put this over here, is going to be my hydrogen ion concentration times my acetate ion. This is for acetic acid. This is vinegar, like you put in your salad dressing. Okay. So there's my dissociation, because remember, we're going to lose that proton off that carboxylic acid. All right, so I'm going to make like a really tiny rice table over here. I'm going to do HA going to H plus A minus here. And in this case, I've got how much? I've got 0.1 molar acid to start with. And so, sorry about that. It's a phone call. Let me turn my phone off. There we go. Okay. So here's my acetic acid dissociating. This is my initial concentration. So I'm going to put that here, and this is 0 and 0. Then I'm going to say, okay, I'm going to be minus X plus X plus X. This is going to be 0.1 minus X, X, and X. Again, look how small this is. Remember, we talked about it being smaller than about 10 to the minus 3 when we looked at solubility in the last unit. So what I'm going to do is I can ignore that. So what that lets me do is say that X squared divided by 0.10 is equal to 1.8 times 10 to the minus 5, where X is the hydrogen ion concentration again, and this is 0.0013 molar. All right, so I'm going to put that in here. I'm going to take the negative log of that, and then my percent ionization is going to be the molarity of the acid, or the amount that ionized, divided by my original times 100, and that turns out to be 1.3%. So I am able to cancel this out. That's what this tells me. It's below 5%. If I just plug in 0.01 and 0.001 here and keep solving, I get 4.2 times 10 to the minus 4, or 3.38 as a pH, and 1.3 times 10 to the minus 4 molar. These are all molarities. And 3.89. The percent ionization is 4.2 here and 13 here. Now, this is kind of interesting because look at what's happening. As I decrease the concentration of the acid, I go to lower quantities or a more dilute solution. My pH goes up, but my ionization goes up too. Why would that be? Why would it be that as I diluted my acid, I'm shifting in that direction? That's what this is telling me. Why would that be? Well, the way to look at this is using Le Chatelier's principle. As I dilute my solution, this is 1 particle, this is 2. As I dilute my solution, the equilibrium is going to want to go towards the side with the most particles. You could also talk about this the way we did by dividing your concentrations in half and calculating Q. But let's do this conceptually this time. I go from 1 particle to 2 because I have a more dilute solution. If I go this direction, I'm making more ions, therefore my percent goes up. This is a really important concept for you to remember for your test, that diluting a weak acid will increase its percent ionization.